In class, we learned an equation that related the speed of a wave to its frequency and its wavelength. We'll start this video with two example problems that will use this equation. The first problem is number 43 from your textbook, and this is slightly different. I made it a little bit more Cincinnati-based, using the radio station Q102. It broadcasts its music at 101.9 megahertz. The speed of radio waves is 3 times 10 to the 8th meters per second, and we're asked to find the wave's period and the wave's wavelength. First of all, it's important to note that you will need to know the prefixes for this chapter, as it's important for frequencies to be given in megahertz or gigahertz. So starting off, we'll convert that 101.9 megahertz. We know mega stands for 10 to the 6th. So that's equal to 101.9 times 10 to the 6th megahertz. Sorry, times 10 to the 6th hertz. Or in proper scientific notation, that's 1.019 times 10 to the 8th hertz. Part A asks us to find the wave's period. Well, one important fact is that the period is the inverse of the frequency, or 1 over the frequency. So I do 1 divided by 1.019 times 10 to the 8th hertz, and that gives me a period of 9.82 times 10 to the negative 9th seconds. Part B then asks us to find the wave's wavelength. That'll use our new equation. Speed is frequency times wavelength, which means wavelength is speed divided by frequency. The speed we know is 3 times 10 to the 8th meters per second. Divide that by a wavelength of 1.019 times 10 to the 8th hertz. Once we divide those two, we find that our wavelength is 2.94 meters. It's a pretty large wavelength, but that's common of radio waves. Notice that wavelength, being a length, is measured in meters. Let's look at a problem that's maybe a little bit less straightforward. This problem talks about a harmonic wave traveling along a rope. It says that it's observed that the oscillator that generates the wave completes 40 vibrations in 30 seconds, and that a maximum on that wave travels 425 centimeters along the rope in 10 seconds. We're asked to find the wavelength. We only have one equation that has wavelength in it, and that's our new equation. Speed is frequency times wavelength. That means that wavelength is equal to the speed divided by the frequency. However, this problem does not give us the speed or the frequency, so we need to calculate those. We'll start off using the information that there are 40 vibrations in 30 seconds. Frequency refers to how many vibrations or oscillations or waves in a time period, typically a second. So, to calculate the frequency, we'll do that 40 vibrations divided by those 30 seconds. You could divide that out first or plug it right into the equation. If you do divide that out first, you'll find that the frequency is 1.3 repeating, and our unit is hertz. Then we need to get on to our speed. The problem also tells us that a given maximum travels 425 centimeters in 10 seconds. Well, speed is constant here, so we know speed is displacement divided by time. So I have 425 centimeters, but I need meters. 425 centimeters is otherwise known as 4.25 meters, and our time is 10 seconds. 4.25 divided by 10 gives me 0.425 meters per second. When I divide 0.425 meters per second by 1.33 hertz, I get a wavelength of 0.319 meters. Hopefully after these two problems, that equation we learned in class is a little bit more clear to you. The last thing we're going to do in this video is learn a little bit about some properties of waves. The first topic is wave interference. When two pulses occupy the same space, we use what's called the superposition principle to determine the resultant pulse. This is similar to looking at a slinky when two pulses overlap. Okay, so let's look at that superposition principle. I have a picture here of two drops of water, and you'll notice that they create waves. There were two drops kind of right in the center there, and we get these ripple waves coming out from that. So looking at these waves, you'll notice that there are areas of light and dark. The dark are areas where there's a trough or kind of the valley in the wave, and the light is areas where there is a crest. Now, if you look at the places where these two waves overlap, there are some regions that are really bright. That means that they're really high. So there's a really high crest in those areas. And there are some areas that are supposed to be bright and aren't. They're on the darker side. Those are areas that maybe aren't quite as high as they would normally be if there weren't for interference. The superposition principle can help us with the two types of interference, namely constructive and destructive interference. We'll start with constructive interference. That occurs when we have two pulses that are on kind of the same side of equilibrium. Their amplitudes are both up or both down. And as we talked about in class, when two waves or two pulses meet each other, they do pass through each other, but we're really focusing on what happens when they overlap. Looking at diagram B in the bottom left, you'll see that these two pulses have started to overlap. And there's this weird bump in the middle. That bump comes from adding the amplitudes of the two pulses in the portions that overlap. Specifically, looking at this portion right here and this portion right here. When I add those two amplitudes, I get what the rope actually looks like. Looking in diagram C, I see that the two pulses are directly on top of each other. Those amplitudes add up, so I get something that's rather large. And then in diagram D, they continue on their merry way, having passed through each other. The superposition principle would help us to be able to figure out the size of that amplitude if we knew the size of the amplitudes of the other two waves. Now looking at the other type of interference, destructive interference. With destructive interference, the amplitudes are on opposite sides of kind of the standard equilibrium line. And you'll notice that rather than having that weird little bump like we had in diagram B for constructive interference, we now have kind of this almost straight vertical rope as it goes from one to the other. In diagram C for destructive interference, when they overlap, we get a smaller pulse, and its amplitude could be found using the superposition principle by subtracting the two amplitudes. And of course, when you subtract, the resultant is always on the same side as the bigger of the two. Now there's a special type of interference called completely destructive interference that would occur if the two pulses had the same amplitude. When that happens, if we had a picture like diagram C, the rope would just be a straight line because the two amplitudes would kind of cancel each other out for a split second when they directly overlap. One result of interference is something called a standing wave. Now, a standing wave is kind of a strange thing. It's a wave pattern that appears to be stationary. So in other words, it doesn't look like it's traveling from one place to another, but rather it looks like it's a constant. Standing waves are actually really important when it comes to musical instruments. It's how musical instruments operate. We'll talk more about that in the chapter about sound. But let's look at some examples of this. So some qualities of a standing wave is that both ends of your medium must be fixed. That means that they're not able to move. Standing waves are characterized by distinct nodes and antinodes. A node is a region of no displacement. An antinode is a region of maximum displacement. Let's look at the two diagrams here and talk about the nodes and antinodes. Looking at the diagram in the center, those are four pictures of standing waves. My top picture has two nodes, one at each end, and one antinode. That's what's in the middle. Even though there's kind of a top and a bottom, we count that as one. The second diagram down, that has three nodes, one on each end and one in the middle, and two antinodes, two regions of maximum displacement. The third diagram has four nodes and three antinodes, and the bottom has 5 nodes and 4 antinodes. Again, you'll notice that these don't really look like the traditional wave like we're used to drawing. Many times when we draw a wave, it looks sinusoidal, but this really is kind of almost like little wave packets in some ways. One last fact about standing waves is that they're only caused by certain frequencies. That frequency, we'll learn in the sound chapter, is related to the length of your medium. You will see examples of standing waves in class as well, so hopefully they'll be a little bit clearer to you when you see them in person.